more to Jim Brisbine from Associated Earth Sciences, who's going to talk about geotechnical considerations.
This is Jim Brisbine with AESI, Associated Earth Sciences. So I'm a geotechnical engineer and a geologist by profession, and this talk will be geared towards the geological and geotechnical aspects of pervious pavement. Some of the highlights of what I'll talk about are put the geological history of the Puget Sound area into context and how that affects infiltration and pervious pavements. We'll look a little bit at the different geological units and how they have pros and cons in terms of infiltration. We'll talk about some of the flow parameters that need to be considered in terms of design, and then we'll finish up with just a few comments about the actual construction, specifically with respect to the subgrades. So to put this into a geological context, this is a great old graphic by the famous mountaineer and painter D. Molinar, where he showed how the continental glacier came down through the Puget Sound Basin during the last ice age and filled the entire basin, covering Seattle, Tacoma, even Olympia, with this thick layer of ice. And you can see the right-hand picture, there's the extent of the ice and then the ice limit. So everything we do in the Seattle, Tacoma, Olympia, all the way up to Bellingham is really affected by this Puget lobe of the continental glacier, and all of the geologic units that we deal with are related to this glaciation. So the result of the glaciation is that we really end up with this classic layer cake. We see this all over the Puget Sound area. When I do explorations, this is the majority of the soil sequences I see relate to this. So the uppermost layer is this recessional outwash material that was deposited as the glacier was receding, and the important point there is that it was never overrun by the glacial ice. So it's a stream outwash deposit that's not over-consolidated. Under that is glacial till. I'm sure everybody's tried to dig holes in their yard to put in plants and encounter glacial till, and it's like a weak concrete. From a foundation engineering standpoint, I love it. When I'm trying to infiltrate groundwater, I hate it. And then below the glacial till layer is this, what usually is a pretty thick sequence of advanced outwash, which has some very favorable properties. So the uppermost layer I mentioned is recessional outwash. This is usually the desirable layer. If you're doing a porous pavement, this is what you really hope to be putting your pavement on top of. And it can range from a fairly uniform sand to a pretty coarse gravel and cobble material. Around here we have what's called the stilicum gravels, which is a recessional outwash, and that's a very cobbly, gravelly material and infiltrates very quickly. Unfortunately, recessional outwash tends to be fairly thin. It's oftentimes not, sometimes it doesn't occur naturally, other times it's been removed by grading operations during site development. But wherever it's present, it tends to be a very good receptor. Underlying the recessional outwash, the lodgement till or glacial till, this is the material that's like a weak concrete. The important thing I'm going to point out here is that usually when we're talking about infiltration rates for say a stormwater pond, if we had 1 to 1.5 inches per hour of infiltration, we'd be pretty happy. With glacial till, you're looking at 1 to 1.5 inches per month. So you can tell there's really just no infiltration happening there at all. So if you're trying to infiltrate water through a pavement on top of glacial till, it's just not going to happen. Below that's the advanced outwash layer, which tends to be pretty clean, pretty sandy, a fairly good receptor. However, it's extremely dense, and that does reduce the overall permeability of the material. It can still function pretty well as a subgrade for a porous pavement, though. We start into a site assessment. We gather information about the soil conditions, the groundwater, all that, try to get a handle on the infiltration properties of the soil, factoring in some things like wetlands and spraying activity. And then one final consideration is we really like to know what the ultimate use of the site is. Where's this porous pavement going to be used? And there's a couple of photos here that really illustrate a good point. Mark, the previous speaker, had a photo of a porous pavement that somebody seal coated on their driveway, which effectively negated any infiltration through the pavement. This is a project we were involved with some years back with a Red Robin restaurant, and they had a porous pavement, but it stopped infiltrating. After some studies and talking to the people at the restaurant, we discovered they were taking their waste grease from their deep fat fryer and dumping it out onto the pavement, and they found that it just soaked right in to the pavement quite nicely and went away. That worked for a few years until they completely clogged up their beautiful porous asphalt pavement section with grease, and then the whole thing came to an end. Our first step in gathering the geological information is to do a subsurface exploration. That can be test pits or borings. This is a typical boring rig operation here. We also look at geologic maps to get a better handle on regional geology. Some critical factors involved in the subgrade for a pervious pavement, the receptor soils, is some of their chemical properties and organic properties. So a typical suite of testing for the subgrade soil would include not just a grain size distribution, that's the basis for determining infiltration rates, but we also look at the organic content and the cation exchange capacity. There are some minimum requirements for organics and the CEC that deal with the filtration aspect of the subgrade. Infiltration testing is the next step in terms of developing an infiltration rate. The old method, when I first started working, we did a lot of double ring infiltrometer tests, a lot of standpipe tests. Small scale, involve a small amount of water. In fact, we'd just carry buckets of water back and forth between a hose and a site, and we're able to run these tests. That's really not acceptable anymore. The new preferred method is what's called the pilot infiltration test, the PIT. It's a much larger scale. The results are much more reliable. Unfortunately, the cost, the time involved is also quite a bit higher. So sometimes we get a lot of pushback from clients who don't want to spend the money. But the simple fact is this is the only really reliable test if you've got a fairly sizable system. And in special cases, you can do just a laboratory grain size distribution. This is the formula down here for determining the infiltration rate. We can derive an infiltration rate using this formula, which we get from a grain size distribution test in the lab. That's very limited, though. It's only allowable for recessional outwash soil. If we're into other types of glacial soils, it's not reliable and it's not really allowed. The old method of using the USDA chart to develop a method is no longer acceptable. Department of Ecology just took that out of the manual in the last few years. These are some shots showing the old methods, the standpipe, and you can see that we're dealing with kind of a small testing area. The surface area involved in the water infiltration is fairly small, and the results are not terribly reliable for that reason. This is a larger scale test. You can see we've dug a large hole in the ground. There's a lot more surface area at the bottom of this, much more reliable results. Another typical installation is to use some kind of a large diameter ring, 5 or 6 feet in diameter, and maintain a water level for, usually it's an all-day process, 6 to 8 hours. But again, the results are much more reliable with this PIT test here. Ecology does put some requirements on sites in terms of number of tests. We use this as a guideline. Sometimes we'll do more. Sometimes we can justify doing fewer tests if we know more about the geology. Modeling, there's a program called MODRIT out there that we use for a groundwater mounding analysis. That's a situation where you've got maybe a few feet of recessional sand over glacial till, the water's not going to pass through the glacial till, so it'll just stop there, and you'll actually develop a mound of groundwater underneath your infiltration facility, the pavement or pond or whatever. So this is a procedure to try to determine how high that groundwater mound would get. In summary, when we're looking at evaluating a site for infiltration, we're gathering information about the geological properties of the soil, the groundwater depths, the depth of unsaturated material that would be acceptable as a receptor horizon, either laboratory and or field tests to determine an actual infiltration rate. Moving on to the construction aspects. As both a foundation engineer and an infiltration design engineer, again, I'm caught in the eternal tug of war when it comes to subgrades. For pavement support, you want as dense a subgrade as you can possibly get. So you encourage compaction to 95% of modified Proctor. You want an absolutely bomber subgrade to support the overlying pavement. When you're looking at infiltration, you'd like that subgrade to be as porous, as permeable, as loose as possible. So we're caught in our own struggle here to maintain pavement support, but also to maintain infiltration for the subgrade. So we're just playing a balancing act in terms of what's the minimum amount of compaction that would be acceptable to support the subgrade. There was a question earlier about whether you could put uncompacted sand below a pavement. We always recommend some degree of compaction for the soil, no matter what it is. However, we'll choose to do lower level, like 90 instead of 95%. Maybe use a static roller instead of a vibratory roller to reduce the amount of densification. But in the end, your subgrade does have to support the pavement section, and if the pavement fails, then the infiltration properties of the pavement aren't really relevant anymore. So we can never lose sight of the fact that we've got to have a decent subgrade out there. We still do proof rolls of the pavement sections just to make sure there's no soft spots. One area of controversy in recent years has been whether to put down a geotextile between the subgrade and then the pervious pavement section. And for a while there were a lot of people advocating the use of a geotextile. In recent years, we're finding that sometimes the geotextile becomes the problem, where material fines will work their way down through the pavement section, hit the geotextile, plug it up, and really become the source of a problem. So the thinking is now that we would use it for separation of differing materials, but use it fairly selectively. It's becoming less and less common that we'll actually see a geotextile used. During construction, the best design in the world for a pervious pavement could all be for naught if the subgrade, the infiltration subgrade, becomes ruined during the construction process. And construction can be a brutal environment when you're trying to deal with something as sensitive as say a sand receptor layer. So you've got things like siltation of runoff material, plugging it up, truck traffic. Just if you're running heavy dump truck traffic over subgrade, it'll densify it to the point where you've drastically reduced the infiltration rate. Concrete trucks washing out their waste material, that will absolutely stop infiltration. We really, during construction, try to take a close look at protecting the subgrade. We encourage the contractor to establish defined haul routes for their truck traffic, so we know exactly where the densification is taking place and the outer areas of the site are being protected. Moving on through construction, as they start to place the ballast layer, which goes between the subgrade and the pavement, again, we encourage the contractor not to run directly over the subgrade if at all possible. Just develop a pad of ballast rock, keep the bulldozer on on the advancing pad so that the tracks never touch the subgrade. And then, as I mentioned before, static rolling as opposed to vibratory rolling. And we find that's a reasonable compromise between the structural and the infiltration aspects of the subgrade. And I believe that's my last slide, so I'll take any questions in the remaining minute or so.
We've got something from LPD. Since the area generally involved in pervious pavement can be large, and even if we don't have infiltration or partial infiltration as low as 0.01, well, that's a long, is beneficial to limit required alternate detention even into fill soils, as many of our sites have been impacted at some point. That is the longest question I have ever seen.
Well, just in general terms, I think we can say that if we're dealing with a porous asphalt pavement, we're talking about a relatively small amount of water over a relatively large area, and that combination does allow us to get by with a lower infiltration rate for the subgrade. So if you compare that to, say, a stormwater detention pond where you've got a large amount of water and a relatively small surface area at the bottom of the pond, you need a high infiltration rate to dispose of that. But that's one of the beauties of a porous pavement system, is that you are dealing with such a large area that your subgrade just doesn't have to be as permeable as it would be for a pond.
How much of the stormwater evaporates off?
That's a good question. I've never been asked that before, and I don't think I've ever seen anything that specifically addresses that. But on a hot summer day, I would think there might be a significant amount of evaporation out of a pavement.